Imagine a system that can observe market conditions, process millions of data points, make trading decisions, and execute trades, all in the time it takes you to blink. That's not science fiction. That's what happens when you combine four powerful concepts that I'm going to share with you today. Good morning, everyone. My name is Alejandro Mancilla. I'm a principal solutions architect at MongoDB. And today we're diving into what I call event-driven AI, a convergence of the OODA loop, event-driven architectures, streaming processing, and agentic AI that's fundamentally changing how we build intelligent systems. From the agenda perspective, we're going to go through some of the topics that we cover here. First, I'm going to start presenting myself and then talking about the challenges that implies building an intelligent system. Uh, then we're going to cover the four pillars that I mentioned earlier. And then we will describe a layer architecture and how Atlas streaming processor uh, becomes the first multiplier. Finally, we're going to cover one particular use cases around predictive maintenance, and we can also cover or share a reference architecture for this use case. Um, so, who is Alejandro Mancilla? Alejandro Mancilla is a solutions architect, as Mara explained, with more than 20 years of experience. And I have a different, a diverse background, I would say, building solutions. Some of these solutions were in the front end, for instance, especially prior to the Ajax type of solutions. We built from scratch one solutions that solves that problem, the communicating between the back end and the front end. Um, uh, then I was also working at Sovergy with building business processes, modeling, implementing those. And there I started working with stream processing capabilities. Um, and now I work with MongoDB, and as you will find out during this session, we have added several capabilities that helps you build intelligent systems. If you want to keep in touch with me, here are some of the contacts that you can use for that purpose, whether it's Twitter, LinkedIn, or even GitHub. So let's start with the fundamental question. Traditional systems are built for yesterday's world. They batch process data hours or even days after events happen. They follow rigid rules that can adapt when the unexpected occurs. And they rely on humans in the decision loop, humans who need coffee, sleep, and vacation time. For instance, last year, I worked with a financial services company that was losing um, several millions because their risk management systems process transactions in 30 minutes batches. By the time they detected anomalies or how the scenarios, the damage was already done. The competitors with real-time systems were eating their lunch. The gap between what traditional systems can do and what modern systems demand is growing exponentially. We need systems that can observe, orient, decide, and act in real time. Systems that learn and adapt continuously. Systems that operate at machine speed with human-like intelligence. So, how do we bridge this gap? It starts with understanding four key concepts that combined create something greater than the sum of the parts. First, let's talk about OODA loop. This framework was developed by military strategist John Boyd. OODA stands for observe, orient, decide, and act. Boyd discovered that in a one-to-one battle, the side that could complete this cycle faster would consistently win. It's not about having better weapons. It's about making better decisions faster. The second pillar, event-driven architecture, instead of systems asking, has anything changed? Every few seconds, events tell systems something's just changed. Immediately, this creates reactive systems that respond in milliseconds, not minutes. The third one is the streaming processing capability. This is where the magic happens. While traditional batch systems is like reading yesterday's newspaper, streaming processing is like having a news feed with instant analysis. Data flows continuously and insights emerge in real time. And finally, agentic AI. These aren't just models that answer questions. They are autonomous agents that can perceive their environment, make decisions, and take actions without human intervention. Think of them as digital employees that never sleep. Each of these is powerful alone, but when you combine them, you get something revolutionary: systems that think and act at machine speed. Here's where it gets interesting. These four concepts don't just coexist, they amplify each other in a continuous cycle. During the observe phase or in the observe phase, event-driven systems capture changes the moment they happen. A customer clicks, a sensor triggers an event, a market moves. These events immediately flow into a streaming infrastructure. During orient phase, the streaming processors transform raw events into contextual intelligence. They're calculating trends, detecting patterns, maintaining temporal windows of data. The AI agents receive enriched, actionable insights, not just raw data dumps. In the design phase, AI agents use this process intelligence to make autonomous decisions. They're not following simple if-then rules. They're applying machine learning models, considering multiple scenarios, and adapting based on outcomes. When agents act, they generate new events that immediately flow back into the system. This creates continuous feedback loops, where each actions inform future decisions. This is how you operate inside your opponent's OODA loop. While they're still processing yesterday data, your system has already observed, orient, decide, and acted on today's reality. Let's concentrate about the technology stack. If we think about in a layer architecture, we can start, for instance, in this case, with the data layer. We use event streaming platforms like Kafka, for instance. These aren't just message queues, they're nervous systems of your entire architecture. Processing layer uses frameworks like Atlas Stream Processing. This layer maintains state, handle complex event patterns, and provide event processing guarantees, even at massive scale. At the intelligence layer, we deploy AI agents using different frameworks. These agents can be anything from simple decision trees to sophisticated neural networks, depending on your use case. Several technologies are important to streaming architectures. Event and data streaming platforms are where it starts. This technology typically aid in the transport and distribution of immutable events that represent information. Apache Kafka is the most commonly used event streaming platform, and is available by many cloud platforms as well. It is important to recognize the difference between event streaming and stream processing. Stream processing is what enables turning those raw events into meaningful business insights or customer experiences. All major cloud providers offer managed solutions for both streaming and stream processing systems and associated real-time capabilities. Stream processing is what I call the force multiplier. In this architecture, it transforms your system from reactive to anticipatory. Atlas Stream Processing is the MongoDB native way to process streaming data that transforms how developers build modern applications. Atlas Streaming Processing It's a stream processing engine that solves the common challenges found in other stream processors. One important thing is it uses the same document data model as MongoDB databases, allowing developers to use the familiar MongoDB Query API and aggregation framework when processing data, either streaming data in motion or data at rest. Another important is that being a fully managed solution, it requires minimal setup, especially if the developers are already familiar with MongoDB Atlas. And it also offers schema flexibility, allowing for stream processing on heterogeneous, rapidly evolving data scenarios. Atlas stream processing works by first connecting to either Apache Kafka or a MongoDB database via change streams at a source. Next, Atlas stream processing provides the ability to continuously process events from Kafka streams or documents from MongoDB databases. It's critical to call out that developers can use the same MongoDB Query APIs and the aggregation framework that they use in their databases. This simplifies the development process for many teams. The same query used in the batch context for yesterday is now a stream processor that operates continuously in a real-time scenario. A couple of important notes on how stream processing works is that in addition to the operators already offered within the MongoDB Query API, Atlas Stream Processing adds new operators, such as windowing functions that are specifically designed and relevant in the context of streaming processing. And lastly, process data is sent downstream to either another Kafka topic using emit operator or into MongoDB Atlas collections using merge operator, depending on the application's needs. So this is an example about how you can identify what are like the different stages that you can work with the Atlas stream processor. In this example, we are seeing how you can connect to a topic. One is this identifier. It is identified as a source. Then we are able to validate the data, whether it complies with some particular requirements or schema. Then we can create tumbling windows where the magic happens. Basically, these windows can create, a specific period of times and analyzing the data while it is being received or ingested. And finally, we are able to connect these insights into other systems, whether it is another Atlas clusters or even send or emit this event or this insight into other Kafka topic. There are multiple use cases where you can use stream processing. Stream processing operate in, I would say, the best scenarios are where continuously data is being updated. The obvious fits for stream processing examples include fraud detection systems, stock market, trading platforms, or as the examples that we're going to cover later on, predictive maintenance. In the intelligence layer, it is important to think about what are right now consider the AI stack. If we think about that, we could identify the application, the toolings that are necessary, obviously, for building these applications, and the computes or the infrastructures. If we deep dive a little bit in this AI stack, we can identify other elements such as programming languages, let's say Python, which is like the most popular. Now there has been another frameworks as well have been created for other languages such as Go or Java. There is also the model provider. This is usually when you interact with another LLM system or the ML model that you design. There are LLM orchestrators as well and frameworks such as Llama Index, LangChain, LangGraph. And Obviously, you will need a database, whether it could help to store operational data and obviously the vectors that you're going to use for interacting with the LLMs. You can also need monitoring and observability tools and frameworks. And finally, you will need tools to deploy these solutions as well. So I'm going to focus just on the capabilities that in this space MongoDB offers with Atlas. Now, MongoDB Atlas natively supports a wide range of functionality, including full text search, semantic search, time series data, that helps you to cover multiple analytic use cases, and now, of course, the stream processing capability. So if we think about the, I would say, the different stages or different capabilities, I would say, that are required in order to build ML systems or AI systems, it covers multiple scenarios. So, for instance, there is the data preparation. There is also the model training stage, and finally, the model inference. All these three scenarios, we can think about how MongoDB can also help you during these three stages. So, for instance, during the data preparation, you can make use of the platform specifically for using the document model. You can receive those elements. You can aggregate. You can the information. You can also clean it. We also offer connectors with a Spark, for instance, if you already have machine learning capabilities over there and you want to build this feature engineering over that. The same would happen if you want to expose or move data from MongoDB to other systems. We can use the Kafka connector. If you are already using Python libraries in particular, we also offer the PyMongo Arrow. And for model training, we also cover other scenarios such as the federated the data federation capability, which will allow you to interact between AWS S3 buckets or Azure cloud storage. The same would happen in the model inferencing. So using the capabilities that now MongoDB has, whether it is for streaming processing or even triggers, we can serve as the operational database that fulfills the low latency requirements for model inferencing capabilities. So if you think in this scenario, what is like the AI flow from the application to the system? So it usually interacts with the database. This information sometimes require other data sources, which will help you to do the data preparation. So you will need these, I would say, tools that can create the flow of the information. You can also sometimes, if you are not needing additional information in the database, MongoDB also provides capabilities for online archiving that you can interact with for that purpose, or you can store using data federation using S3 data. For then the model training, finally the model registry, and eventually the model inference. So all I would say those are like the major elements in the AI architecture or intelligent system. So if we think about also in the event-driven AI scenario, such as the one that we are going to cover, so we have the message queue component, we have the application database, the cold storage, data lake, streaming features such as a streaming processing that we will cover for model inferencing, and then we can create obviously these real-time predictions based on the events that are happening directly. These events are not also useful for serving, I would say, the insight that are happening right now, but it could also help you sometimes to store new events and train this model in a more dynamic pace as well. So the scenario that I want to highlight in this case is the predictive maintenance. So MongoDB Atlas can help you to power end-to-end predictive maintenance solutions. This scenario, we can identify different stages. So the first one is the machine prioritization and criticality analysis. This will help us, to address the question, which machine should I prioritize for predictive maintenance and why? Usually, in this case, machine learning and RAG-based architecture are critical for this solution. The second stage is the failure prediction. This is where you can answer the critical questions. What is the root cause of imminent failure? And this is where the magic happens with Atlas Stream Processing. You can process the real-time sensor data and enable early detection of potential failures before they occur. Then in the third phase, we have the maintenance plan generation. Now that we have these insights, obviously now we have to understand based on the knowledge base that we have, which are mainly sometimes are, all these manuals that we have for these different components or devices, and then automatically generates a detailed plan about how we can repair, or what is the procedure for repair this particular device. And in the final stage, there is a maintenance guidance generation. So now that we have this information, how do I get better guidance of fixing machines? This will help us to provide enhanced maintenance guidance by integrating service nodes and repair instructions, where are, not just directly from the manual, but with other technicians that had provide or solve similar problems. So if we think about this rack architecture that I mentioned before, you can identify two types of input data. There's the structured data, sometimes, information regarding production parameters, machine breakdown frequency, all these events that are being sent. But there is also unstructured data, institutional information regarding the knowledge or the manuals for these devices or machines. The workflow aggregates and operationalizes both data types using vector embeddings as well. There are some of capabilities that now MongoDB also supports. And using vector search, we can perform semantic search to provide relevant context to an LLM. This could be using any LLM framework, or even solutions such as Amazon Bedrock or Cohere in this case, which generates the contextual response to prioritize these queries. This helps maintenance teams make data-driven decisions about which machines need attention first. These are real-time architecture process machine sensor data through 6 stages: data collection, stream processing, data storage, change detection, and ML inference. All of these components are the solution that we can provide for this use case in particular. So before finishing, I want to highlight what are the strategic advantages of creating intelligent systems using streaming processing or event-driven AI. The first advantage is obvious, is speed. It's about being consistently faster than your competition. When you can complete your OODA loop in milliseconds, while your competitor needs minutes or hours, you're not just winning, you're playing a different game. Second, it's these systems adapt continuously. Traditional systems break when they encounter unexpected conditions. Adaptive systems learn from them. Then there is the streaming pattern analysis, which enables a prediction. You're not just responding to what happened, you're preparing for what's likely to happen next. And finally, you reduce human error and increase consistency. Your system doesn't have bad days, doesn't get tired. and it's basically available for you all the time. Um, so what is the recommended implementation approach for this scenario? Usually we recommend phase by phase. Don't try to build everything at once. Start with an event-driven foundation, a basic streaming, prove the concept, then expand. The phase one, you can get your event background working. In the phase two, you can add the stream processing for pattern detection. Then you can integrate AI agents for decision making and optimize your OODA loop speed and feedback mechanisms. And finally, the key success factors start with clear use cases and success metrics. Build incrementally and validate at each phase. Invest heavily in monitoring and observability as well. You can optimize what you can measure, and plan for continuous learning and adaptation from day one.